So I'm Gergö. I'm a postdoc at Inria, which officially means the French National Computer Science Research Institute. But I've learned since yesterday that to many of you, Inria means the people who develop Poly. I'm not one of those people. I'm one of the people who work on CompCert, the formally verified C compiler, which is cool too. And as a side project, I have this thing about comparing compiler optimizations. I have a GitHub page dedicated to this work, which you can find by typing the words missed optimizations into your favorite search engine. It should be the top hit. And there you will find all the examples that I will show you and a lot more, and some slides and a paper. Right, so the question that I wanted to investigate is, do our compilers always optimize well? And the answer is no. So we know that in general, an optimizing compiler will give us better code than a non-optimizing version of the same compiler, but that doesn't mean that every single thing that it does is actually as good as it should be. Maybe it forgets to optimize something, maybe it tries to optimize something, and in doing so generates code that is worse than what you had before. So I wanted to sort of study things like that, and I wanted to do this by comparing the code that is generated by different compilers for the same input program, so C compilers, C code. But I'm lazy, so I didn't actually want to look at this code myself. So I developed this little toolchain that looks at the code for me and gives me back minimal test cases that show some optimization that one compiler managed to do and another one apparently failed to do. I applied these tools to 3 C compilers, GCC, Clang, and CompCert, the formally verified C compiler. And I found a bunch of issues in peephole optimizations, instruction selection, register allocation related stuff, dead stores to the stack, GCC likes doing that, copy propagation issues, and so on. So I will start with 2 examples, just to show you what kind of stuff that I can do. Here is a little C program that was produced by my toolchain automatically. So this is a C function that takes 2 int parameters p and q and returns the value of q plus p modulo 6 divided by 9. And now we will look at the machine code generated by 2 compilers for this code. So I will have to show you assembly code. I will show you ARM v7a assembly code. I assume that you are not expert in ARM, so I will try to explain everything you need to know. And all of the code that I show you is compiled at -03, so we would expect it to be optimized. Okay, so this is what Clang does on this input code. Do not try to understand this in detail. Just follow the colors. So we have a blue block of code which corresponds to the blue operation, which is taking an integer p modulo 6. And then there is a brown block of code which corresponds to the brown operation of dividing something by 9. Both of these use a certain well-known magical recipe that you can apply if you have a division by a constant. In that case, you don't actually have to emit a division. You can do this magic multiplication by something and then some bit fiddling, and you will get the same result as you would have gotten with a divide, but it's much faster. So this is a nicely optimized modulo, a nicely optimized division, and a very nicely optimized addition. Comments so far? Okay, here is the code generated by GCC. So GCC does some math. If you take p modulo 6, no matter what p is, the result will be in the range -5 to +5. And if you take any number in this range and divide it by 9, then according to C semantics, the result will be 0. So this input code, q plus something, is equivalent to return q plus 0, which is simply a copy of q from register R1 to the return register R0. Right. I filed a bug report. No, I put this online. Somebody else filed a bug report for LLVM, and this was fixed. It turns out that LLVM was already able to do this for unsigned integers, but not for signed integers. And so this was fixed using a well-known software engineering methodology known as copy and paste. It's in the instruction simplifier, and now Clang generates the same code. Here's another example. This is a function that takes a double, which is called C for some reason, and 2 pointers to int p and q. It converts the double to int, and puts the value into a local variable I. Then it stores I through the pointer p and stores it through the pointer q and then returns it. So the code generated by GCC for this is 4 instructions. The first one is a VCVT. The CVT on ARM means convert, and the V prefix on ARM always means floating point, so that's very simple to remember. So this is the conversion from double to int. Then we have a store. Then we have a move that you can ignore if you don't want to think about why it's there. And we have a second store for this instruction, and that's it. Okay, what does Clang do? Clang does a conversion. Clang does a store, very nice. Then Clang forgets that it has just done a conversion and does it again. And puts the result in the same register where it put it before. So it overwrites a certain bit pattern with the exact same bit pattern. Then it forgets again that it has done the conversion. This time it puts the result into a different register just to increase register pressure. You can never have enough of that. And then it does a move and a store. I filed a bug report for this. Somebody looked at it and said, okay, there are redundant rules in the instruction selector for this VCVT instruction, and we can remove them, and then this goes away. And then 3 weeks later, somebody else came along and said, yes, but that breaks something else, so it was reverted, so you can still get this with Clang if you want it. If you don't, you can use GCC. Right. Okay, so how does this magical tool work? It uses a method called randomized differential testing, which was developed originally for testing compiler correctness. And I just use the same thing, and instead of correctness, I test for optimizations. So you start out with a random code generator. There is one called csmith, which is very nice. There's another one called ldrgen, which I developed for this work, which is also very nice in a different way. And there are a bunch of others. What they do is they give you some source code, some file containing a C function. You take this code, you compile it with 2 different compilers. They usually, hopefully, give you 2 binaries, 1 each. And then you compare these binaries and see if there is some difference between them that interests you. So if you are testing compiler correctness, the difference will be, do they have different semantics for a well-defined input program? For me, the difference will be in optimization, and I will explain how that works. So if you don't have a difference, okay, well, you throw this one away, and you start with a new randomly generated program at the top. If you do have a difference, you have to ask yourself, is this C program small enough that I could show it to a compiler developer? I'm not sure what's going on here. Usually it isn't. These generators generate hundreds or thousands of lines of code, and nobody wants to look at that. So you have to do something about that to reduce it to a nice and small example like the ones that I showed you before. And for that, there is a tool called creduce, which is pure magic. It is awesome. And what it does is it takes these hundreds or thousands of lines of input code and reduces them to 5 or so lines that have the same behavior that you're testing for. So what creduce will do is remove some parts of the source code, remove a statement, remove some tokens, or do something semantic like replace a variable by a constant. And then it will do the same compilation and comparison steps as before. And if you still have the same interesting difference, then it will keep reducing. Otherwise, it throws away the current candidate and tries another one. And it works really, really, really well. If you do any kind of compiler testing, I recommend that you use creduce. It's awesome. Okay, so how do we test for interesting differences in optimizations? I developed a little tool that I call OptDiff to find optimization differences. I do that using binary analysis. So this is a little tool that takes two binaries and compares them, except that it doesn't really compare the binaries, it just computes some number that I call score for everyone, and then it looks if these scores are equal or not. And if they are different, then I say, well, this looks like an interesting difference. It's based on a framework called Anger for binary analysis. It was developed for security analysis, but it's flexible enough to allow me to do this work. It's a multi-platform tool. I mostly tested ARM because ARM is the assembly language that I can read. I did some testing of vectorization on x86, and I could do other architectures as well. And this Anger framework is written in Python, so my tool is also written in Python. So how does this work? To analyze a binary, well, I load it. I have Anger compute the CFG of the binary for me. So I assume that there is a single function in there. I do some really simple estimation of basic block frequencies. And then I applied little functions that I call checkers, which look at every instruction in isolation and compute a score for every instruction. And so I apply C, a checker C, to every instruction, and I sum up the scores for all the instructions. I weight by these basic block frequencies that I computed before. I sum up for every block, and that gives me sort of a total score for the entire binary. And so all the intelligence in this tool is in these little checker functions, of which I have different ones. For example, there is one for counting the number of instructions in the binary, which is already good enough for finding differences like the first example that I showed you, where a client generated 14 instructions and GCC generated 1. That's an interesting difference in the number of instructions. You can search for, basically count memory accesses, stack accesses, function calls, certain kinds of arithmetic instructions, vector instructions if you're testing vectorization, that kind of stuff. So this is really very, very simple. And the checker looks at every instruction in isolation. There is no propagation of information between instructions. There is, it does not take into account the instruction schedule or anything like that. I wanted this to be as simple and primitive as possible, and I managed to do it, to have it really simple and primitive. Right, so what do these checkers look like? They are little checker function, Python functions that you annotate with this magic checker decorator, and that take an instruction basically and return a score for this instruction. So if you just want to count the number of instructions in your program, you return 1 for every instruction, and this will be summed up correctly and give you the total number, weighted by expected execution frequency. Here is a different checker that I use to count memory loads. And based on this, I then have a checker that counts the loads from the stack that I can use to test the quality of register allocation. So what this does on ARM, as ARM is a load store architecture, to find a load, all I need to do is to look at the opcode. So this says, well, there is a load double word instruction in ARM, which loads 2 things from memory, so I will give it a score of 2. There is a load multiple instruction, which takes a list of registers to load, and the length of that list determines how many things to load, so I compute a score depending on that length of the list. And otherwise, I match this regular expression against the opcode, and if it matches, then the score is 1, so it's a load, otherwise it's 0. If you look at this, and you think, well, this is really ad hoc, this is a really dirty hack, that is true, but it's good enough to find interesting stuff in production C compilers. So if you make your compilers better, I will make this better. Also for x86, you would have to do something else because it's not a load store architecture, so you would have to, you cannot match on the opcode, but there are ways to treat that. Right, so some more examples, because that was all the theory that I have. Here's a little function that takes 3 doubles and computes minus P1 minus P2 times P3. Turns out there is an instruction for that on ARM. Floating point negated multiply add. Clang didn't know that it could select this instruction, so it selected a negate and a multiply and subtract instead. Because in fact, it knew to select this VNMLA instruction for minus A times B minus C, but not for minus C minus A times B, which is the same due to a commutativity-like property. So I submitted a patch for that and it was merged. So I'm officially an LLVM developer now. Okay, this one is fun. Register allocation. This function takes a bunch of doubles and it does a bunch of double arithmetic. It's a bit bigger than the examples before because you have to build up some register pressure if you want to test register allocation. But it doesn't do a lot. It's straight line code. There are no pointers or anything. But in fact, yeah, the details are not very important, so I will grayed out. Let's look at some of this code, and in particular, let's look at this instruction here. This is a spill. So somewhere in this code, the register allocator decides that it has no more free registers, so it has to spill something to the stack to free up a register, so it can use it for some computations, which is okay, which is what the register allocator has to do if there are actually no more free registers. Turns out in this case there are at least 3 that it could use, or so it seemed. So D13, D14, and D15 are each used very briefly above this point and then never touched again. So they would be free at this point. Each of them could be used instead of spilling D6, but for some reason they weren't used. So I did a bug report for this, and somebody pointed me to the real cause, which is not register allocation, it's instruction scheduling. If you turn off the post-register allocation instruction scheduler, you will see that this is not at all the code that is exposed to the register allocator. What the register allocator sees is a really, really bad schedule in which all of these live ranges overlap, so it really has to put everything into different registers and has to spill one register. And then if you do allow post-allocation scheduling, then that scheduler will go back and give you a good schedule and sort of cover up the mistakes of the previous one. So it looks like the default pre-pass scheduler for this flavor of ARM is not a good choice. And discussing with some ARM engineers, and I think they should try to change it and run their tests and then find a better default scheduler for this. But I haven't managed to convince them so far. Okay, another example. Again, purely floating point calculations, straight line code, nothing very complicated. Here is the code as generated. Here's the start of the code as generated by GCC. So it generates an add for this thing here, and a multiply for this, and a subtract for that, and then some other things. Clang does the same, except somewhere in between it decides to permute 4 registers for no discernible reason. So it copies D7 to D10, which is nice. It frees up D7, so you can copy D5 to D7, which is cool because it frees up D5 to... You may be thinking that this looks silly, but it's a cool setup for some really cool optimization that comes later on that I'm hiding here, but no, unfortunately not. It just has these useless copies. Here again, if you choose a better pre-pass scheduler, then this goes away. So this seems to be the same issue as before, but I didn't know that at the time I made the slides, and also it's fun to look at. Right. What else? Okay, for some reason I put LLVM and other compilers into the title. So I'm showing you a missed optimization in GCC and then one in CompCert. And then we're almost done. So here is a function that contains a little for loop, which is written as a while loop, but it's really a for loop. It counts a variable I from 0 up to some n, which is a global, and never changes. And it does some sort of little reduction on I in the loop. So this is a textbook vectorization example. Should be vectorized. And it is vectorized by GCC. Great. Unless you use a version that came out after late February and before late March. So sometime in February they changed something in the GCC vectorizer, and it forgot how to vectorize this loop, resulting in a 1.8x slowdown. And by accident I stumbled upon this and did a bug report, and it was fixed within a few hours. So this was important to the GCC developers. The problem here was also very interesting. So GCC knew that it was legal to vectorize this function, but it did some sort of cost-benefit analysis. And in this analysis, it assigned cost of 0 to many operations that do not really have cost of 0. And then, so basically, it thought that it would no longer be beneficial to vectorize this. But after my report, they applied a 2-line patch, I think 1 line of which was a comment, and this works again. So that's great. Okay, CompCert, the formally verified C compiler. If you take this function, which takes an int a argument, it computes the following. If a plus 42 is not equal to 0, then do nothing. Otherwise, do nothing. And then return 1. A good compiler, an optimizing compiler, should just translate this to a return of 1. So move the constant 1 into the return register and you're done. CompCert didn't quite do the same thing. It didn't generate the sort of redundant jumps that you might expect, but it did evaluate the branch condition and then didn't do anything with the result. And this was fixed. We were discussing this internally, and I said, oh, this is stupid, nobody would write code like this. But I was told that in embedded systems, many people use model-driven code generation tools that like to generate this kind of stuff. So it was important for us to fix it, and at least this simple case is fixed now. Right, so overall, I tested 3 C compilers with my tools. Here's a little table giving you some numbers on what I found. So the first column is the number of distinct things that I found interesting enough to put on that GitHub page there. The second column is the ones that I found additionally interesting enough to actually either report in a bug tracker or submit a patch for them. And the last column shows you how many have actually been fixed. You should not try to compare rows of this table and come to conclusions like CompCert optimizes as well as Clang, or CompCert optimizes twice as well as GCC. This is not quantitative data that would allow that sort of interpretation, and it was never meant to be. As you can see, not everything that I found I bothered to report, and not everything that was reported was actually fixed. Unsurprisingly, these things generally don't have very high priority, which is fine. I understand. In fact, I could have fixed a bunch more in CompCert, and I didn't because I had other stuff to do as well. When you run my tools, you find a lot of duplicates. So usually you have to play a bit with the configuration options to get new stuff. So you have to be a bit creative to search for new issues. But overall, you don't get the same thing, the one missed optimization over and over again. So it's not like that. It has some limitations, this tool. The main limitation is that C-reduce really likes to turn loops that terminate into loops that do not terminate. And infinite loops are optimized differently by GCC and Clang, so it's hard to test code containing loops. Which means that the popular question why I use randomly generated code instead of real-world benchmarks can be answered by, well, I have problems with a loop termination. For some kinds of loops, you can get around this with some analysis, but what I would really like to have from compiler developers would be a warning flag that I can use to ask for warnings about infinite loops, because then I could throw away all of those mutants that I'm not interested in. Right. Well, here's the summary. So you can compare the code generated by different compilers to find missed optimizations. You don't have to do this manually, you can use tools. Using mostly off-the-shelf tools, plus one that I should really release soon as open source. I have used this toolchain to test 3 compilers. I have found some interesting issues in all of them. And I have this page, again, that you can look at to find more examples of missed optimizations. One more thing. I'm on a job market, so if now you feel like you want to give me money, we can talk about whether I want your money or not. Thank you.
We have quite some time for questions, so yeah.
Thank you for presentation. I'm compiler engineer from ARM. I'm really impressed how many things you found. Question, so because we have optimization pipeline, we have backend, middle end, and they operate on different IR representation. Why don't you use IR to find what is actually missing in the middle end, and machine IR to check what is missing in the backend?
If I wanted to compare the IR of GCC and Clang, I would need tooling for that, I think. There is a Dragon Egg, which I guess might be usable as a translator between the 2 IRs. It could be a possibility to use that to compare mid-end level optimizations. I haven't done that yet. So the easiest way to do this is to take a standard input language, which is C, and take a standard output language, which is assembly, and to compare that. But yeah, you could do more fine-grained stuff if you could compare IRs between compilers. Another thing you can do is, when I say you use 2 different compilers, it doesn't actually have to be 2 different compilers. It could be 2 different versions of the same compiler. So you could be testing for regressions. And for that, you could have an LLVM-based toolchain that sort of takes an LLVM from a month ago and the current version and compares the IRs. So there are ways to do that I haven't explored.
Thank you.
So it's funny that we are doing exactly the same thing you're doing, and we came to the same conclusions about IR and assembly. So our tool, instead of analyzing binaries, it analyzes the assembly, and we asked both GCC and LLVM to produce verbose assembly. So GCC tells us when it spilled, why it spilled, and etc. So we can actually get all of those metrics kind of for free from the assembly annotations that both compilers do. And we're also thinking about doing this on IR level for LLVM specific things. But instead of auto-generating, we're doing known benchmarks. So we just look at the bigger picture rather than the smaller picture. So I think we should collaborate because we have the exact same goals.
Okay, yeah, that would be very interesting in doing that. Thank you.
Thank you. Any more questions? You got enough time? Last chance? Okay, if not, let's thank the speaker again.